everyone. My name is Oya Demirbilek, and I'm a professor of industrial design at UNSW. And on behalf of the Industrial Design Program, I would like to extend a warm welcome to all of you joining us this evening for us, and it might be morning for you. So I welcome you from the beautiful Bijiko country where I live and acknowledge the Bijiko people who are the traditional custodians of this land. I would also like to pay my respects to elders, past and present, and extend that respect to all other indigenous peoples joining us today. So again, I checked this morning in LinkedIn and there were 237 attendees registered from different places around the world, and that's so exciting. So welcome, and thank you for joining us for our fourth talk already of Stories Behind Products. So as most of you would know, these talks are quite fluid. You can ask questions via the chat function, and Michael will answer them after his talk. And if we go over time, we will make sure your questions are answered in LinkedIn. So today we are proud to have Michael Thorogood, an industrial designer living in Australia. So welcome, Michael. Michael is currently working at Breville, an Australian publicly listed company with a group of global subsidiaries leading small electrical appliances in the consumer product industry. And Michael is a senior industrial designer, and I heard soon to become industrial design manager. And before joining Breville, he worked at Vert Design for 5 years. And before that, he was a freelance designer. Michael studied industrial design at the University of Newcastle, and he told me he has always loved making, building, furniture making, and joinery. And this evening, Michael will present the Smart Oven Pizzaiolo, the first domestic countertop oven that can reach 399 degrees Celsius and cook an authentic wood fire style pizza at home in just 2 minutes. So over to you, Michael.
Awesome. Thank you, Oya. Thanks, everyone. Nice to meet you all. Let me share my screen. How's that? Is everyone okay? Cool. Thanks so much. Okay. As Oya said, sorry, I'm Michael Thorogood. I'm an industrial designer, and today I'm going to be talking to you about the story behind the Smart Oven Pizzaiolo. So I was the lead industrial design for this project. And I guess while this is almost like my third child, this project or product. And I think industrial designers are an amazingly capable and sort of well-rounded, skillful type of person. I think I wanted to make it clear that whilst I'm telling the story, I certainly was not alone in creating this product. There was a really big team behind it, which was a mix of other industrial designers, mechanical engineers, electrical engineers, software developers, test kitchen or kitchen experts, marketing people, IP people. Like, it was a really diverse team that was behind this whole thing. So I'll certainly be telling you what I experienced, but yeah, maybe people who haven't had a lot of experience with developing bigger products, like, there's a lot that goes into it. So I think this is kind of useful and interesting to see the amount of people that go into this. And before I get started specifically on talking about the pizzaiolo itself, just a couple of bits of information that could help provide a bit of context. Some of this people will know, maybe not everyone. But in terms of developing an oven, there's there's 3 different heat transfer mechanisms. So you've probably heard of some of these. There's convection, conductivity, and radiant energy at play. Convection is the energy transfer through a fluid, and you can think of that if you go outside on a hot summer's day and you feel like westerly wind. That is convection energy. So energy through a fluid, being air in this case. Conductivity is the energy transfer by direct contact between bodies. So if you're sitting on a cold seat and you can kind of feel that cold through your pants, like, that's conductivity. And radiant energy is the energy transfer via a body emitting electromagnetic waves. And if you went outside on a nice sunny day, it's that sort of sunshine hitting your face. That's sort of radiant energy. So developing an oven, we're looking at kind of making use of those 3 different types of heat transfer mechanisms to, combine and kind of, orchestrate those things to get a desired food result. It doesn't get too much more sciencey than this, so this is the worst of it, I think. And for those who have developed appliances, you'll be well familiar with this, but for those who aren't, when you're developing an appliance to run at a consumer's home, there's limitations with how much power you can withdraw from a wall socket. In 240-volt countries like Australia, New Zealand, other parts of Europe, that means you've got a maximum of 2400 watts that you can withdraw from that wall. In the US and Canada, it's slightly different, where you've got a maximum power of 1800 watts. If you withdraw more than that, you'll have experienced it where you've got multiple appliances running in your kitchen, and you might trip a circuit breaker. So the safety aspects of your house are going to prevent you from kind of withdrawing more power than that. So there's just a couple of things that they'll come up again, but if you're not familiar with this kind of thing, they're useful little bits of knowledge that will help you understand some of the stuff later. One of the first things that we did when we were developing this product was try and establish some really clear and understandable food goals. And thankfully for pizza, and particularly this style of pizza called pizza napoletana, there's literally a rule book around what pizza napoletana should be. There's an association over in, I believe, Naples, and they've got a rule book, and they mark, there's pizza competitions where they go and mark against criteria against what the characteristics of the pizza should be, the dough, the pH of the sauce. So there's an extensive kind of rule book. And we looked through that and took out some of the characteristics that we were looking for. And those things were that the dough, after being cooked, should still be soft and elastic and easy to manipulate and fold. And then in the case of pizza margarita, which is your classic tomato sauce, mozzarella and basil, that the mozzarella should appear kind of evenly spread. And then the basil should be still green effectively, like a little bit darkened, like kissed by the heat, but not absolutely obliterated. So we took some of those things as little keys that would help us judge how we were tracking when we were testing different things. What those things might look like on a pizza, this is an example of a Margarita Pizza, where the base is cooked at a high enough temperature where you'll get that characteristic charring on the underside. Around on the top, around the edges, you'll get, again, that charring, but it's called leoparding or leopard spotting. And then the interior of the pizza, so the cheese is kind of melted, but not to the point where it becomes a hot mess. And the basil is still green. So when you're looking at a pizza, you can start understanding what's going on in terms of the oven, like how that heat and that energy is being applied to the pizza, and whether it's being applied appropriately or not inappropriately. And we knew to do that, to get those kind of characteristics, we needed to be cooking the pizza very quickly. So this was a really early bit of work where we were trying to describe the difference between a pizza cooked in 2 minutes versus a pizza cooked in 5 minutes. The pizza cooked in 2 minutes was sort of soft, elastic, malleable. It had those kind of characteristics of charring and leoparding that we wanted, whereas a pizza cooked in 5 minutes, basically the moisture or the hydration in the dough had been cooked for long enough that was all driven out, and you ended up with a biscuity kind of texture. The sauce had reduced and become more acidic. So certainly there's a place for this type of pizza. And on our pizza oven, we have longer, slower cook times. But for pizza napoletana, they're not the characteristics you're looking for. So we knew we had to do it quickly. And doing it quickly meant doing it at a really high temperature. This is just a simple graph sort of helping you understand how hot we are compared to conventional cooking. So down the bottom, in the area of 120 to 240 degrees, you've got a lot of the kinds of foods that you might be typically making at home. So if you're baking cakes or roasting meat, roasting vegetables, you're typically, working at around that 180 degrees. That's the sort of oven default. You might want to go a little bit higher than that if you're cooking bread to get sort of a bit of oven spring. And really, most conventional ovens will max out at 250 degrees. They won't let you go above that because it's not safe for the appliance to do so. Some will go to 300, but really most of your baking and cooking kind of occurs in that 200 sort of area. Neapolitan pizza is way above that. So really to do true Neapolitan pizza, you're looking at 380, 400 degrees, even slightly over. And in context to ovens, that's around the same kind of area where pyrolytic ovens come in. So they're the ovens that have doors that lock. You can set a cleaning cycle and the oven kind of incinerates all of the burnt on, oil and debris and carbonizes it. So that's the kind of area that you're in terms of where we need to be cooking pizza Napolitana. So it's a world apart from where we typically operate. Now, where this project began, there's a series called Modernist Cuisine. So this is a book series, and they do a really great job of, talking about the science behind food and some of the science behind different techniques. There's a whole, series of like different techniques and volumes. They've done actually a pizza series just recently. And one of the articles in their first release describes how you can, work with your existing oven, but, hack it a little bit to help you achieve more wood-fired like oven performance at home. And what it suggests you do is get a piece of steel up to 20 millimeters thick, so nearly an inch thick piece of steel, put it in the very top rack position of your home oven and preheat it for, I think it's an hour. Like just basically soak it with as much energy as you can. Then the moment before you go to launch your pizza or slide your pizza into the oven is to change the setting on the oven so that then your top element or your broiling element comes on. And what that's doing is you've got a steel that's kind of absorbed all of that energy, like a thermal battery, that will then cook the underside of your pizza when you slide it on. But then you're making the most use of the available power going straight to that broiling element. So you're getting the most radiation you can. And that's kind of a fudge to get you close to, Neapolitan pizza. So we were reading this article and we knew people love pizza. Like that's, I'm not just saying it, like it's a pretty well-known fact. And really achieving Neapolitan pizza at home up until that point was basically unachievable. With the exception of if you went down the path of deciding to build a wood oven at home, absolutely you can go and do that with a bit of skill and a bit of time. But they're particularly expensive. They're beautiful. I love one, but they're a whole art in itself operating one of those things. So that aside, it's kind of impossible to achieve pizza Napolitana at home. And we thought it could be something really exciting to be able to combine maybe what we've learned or that theory of preheating steel and switching power around to allow people to be able to cook this at home, which previously they hadn't been able to do. So my first day at Breville looked a little bit like this, where I was given a really simple and clear brief, and that was to cook a 2-minute pizza. There'd been some work done before as to how we think we might be able to do that. And what this describes is on the top line, that's showing you how our existing pizza oven operates. So this little grey oven here, this was existing in the market, and it has a pizza stone, and then above and below that is a heating element. During its preheating phase, both elements just go on as hard as they can go, preheating the stone. You'd go and launch the pizza, and again, the same two elements carry on heating. And really, the best you get is probably about a 5-minute pizza. Again, that's completely fine for some styles, but it's not going to give you the type of pizza that we were chasing. What we thought we might be able to do or base a product on is the same kind of technique as was described in Modernist Cuisine, where we would preheat a stone or a base, and then when you went to launch the pizza, was flick the power to the top side to sort of replicate that technique. And we thought that there was probably something, a product that we could develop and something that would be really interesting to people. What we ended up doing, this was the first proof of concept model that was developed before my time. And this operated in that same way. We had an aluminium plate that had a heater attached to it that was preheated. You'd launch the pizza in and then flick one of those switches on the side to then transfer the heat up to the top. And it worked really well. Like, it was good fun and such a cool utilitarian thing. So the next little while of my Breville career was a proper deep dive into pizza techniques, looking at different recipes online, talking to anyone, looking at different pizza styles from around the world, seeing what competitors were doing, looking at different technology that was available, like understanding the compliance requirements for, an oven that got way hotter than what we were typically used to. Loads of testing, developing, pizza making skills, and just generally learning about pizza in general. So it was really rapid. It was a proper deep dive and just obsessing with pizza. At that time, we just got a new CEO. So we had his presentation to the new CEO describing kind of what it is we'd come up with and what we were going to do. We had a workshop with Heston Blumenthal, who came over with his development chef, and we kind of showed off our tech and, bouncing ideas back and forth. We presented to William Sonoma, who's a key retail partner for Breville, and kind of just generated all this hype and excitement about the whole thing. So with all of that behind us, we had preliminary IP filed. We had our proof of concept in the form of this model. And then we got the blessing to form a big team, put together a really aggressive schedule, and secure the best manufacturing partner that Breville had. So there was a lot of sort of momentum and sort of speed behind this thing. We then organised a trip to go and kick off the project with the manufacturing partner. Ahead of that, ordered all these ingredients to be imported from Hong Kong to be ready for us when we got there. Had all this equipment delivered so we could go and demonstrate and show off this thing. And day one over there, we kind of had everything lined up. We did all the formalities and kind of talked about the project, and then it was my turn to go and demonstrate this thing. So we turned it on, preheated, got all the dough ready and kind of explaining how to make pizza. And then went to go and flick the switch to kind of change the power over, and it blacked out. So nothing happened. Like, it just power off. We're like, okay. We tried it again, preheated, and it was all okay. And then again, went to go and launch the pizza, and power off. And we didn't know why. So the room didn't go as we were hoping for. And it looked a lot like this, where we were kind of discussing ideas and kind of trying to troubleshoot what was going on. Everyone was kind of looking at the team like, what's happening? And what we uncovered was that if we go back to the brief and the idea that we were working with, rather than preheating with 1800 watts, flicking it over, and then cooking with 1800, the way that prototype was built meant that we were actually cooking with 2400 watts. Which, if you go back to the limitations in the US, that's exceeding what's allowable. So the power supply in the factory, which was set to be sort of testing US equipment, it wouldn't allow us to pull that power. So just because of the speed we were running at, we missed it, and then we had a problem to solve. So, the first step was just looking like, could we get away with 1800 watts? So we dialed it down. The food result was unacceptable. So the challenge then became like, how do we find 600 watts? We lost it. So that's a proper design challenge. Then that week was a lot of this kind of thing, where we were trying to figure out, just, almost design the product from ground up again, working with what we already had in the form of prototypes or equipment there, what they had already made, and what we kind of cobbled together. Formulating test plans and prototyping plans. Like, if you do this and then this, we'll come back the next day and we'll have a look at that and test this, and then we'll try and learn something. So lots and lots of rapid kind of talking about what we might be able to do, how we could configure this, and trying to figure out how we can get 600 watts back. The types of prototypes we put together in that week weren't pretty, but we learned something from them. Most of them didn't work. This was an example which kind of looked pretty Frankensteinish, where we took a couple of fry pans, electric fry pans, machined them down, made a sort of housing around them, and assembled heaters, and we could kind of turn different things on and off at once, going to try and, the same kind of principle where we're shifting power around. A complete failure, but things were melting, and it just didn't work. But this was the kind of week where we were just sort of building things rapidly, just to kind of try and find something. One of the things that we did, so rather than trying to find 600 watts, which you can't do, we decided that we needed to be optimizing the space that we had to making the power we had the most effective. So that was kind of reducing dead space. So you can see that image on the left, rather than having, this is like a plan view of the product, rather than having just a rectangular cavity when you're cooking a round product, pizza, we decided to make the back of the product round. So you're kind of eliminating maybe 20% of the space that you just don't have to heat up. So you're making the power that you've got the most use of it. Also, pizza's pretty low and flat. So we were bringing the top elements down closer to the pizza to the point where they become really effective. So just starting to optimize the cavity to be suitable for a pizza with the amount of power that we had available. Then going over one of the weekends, we went back to Hong Kong. We ended up going to a pizzeria, which as a team, and just, it was kind of one of those subconscious things, like looking at the food and things kind of keep simmering away. But we had this idea to make use of the existing pizza oven kind of just as a kind of chassis to work with, but then place a circular heater like kind of at the edges or at the edge of the ceiling. And whilst the pizza shown here it's not the prettiest pizza you'll ever see, this was like one of the things that kind of, we knew that we were onto something. Like, it had all the characteristics you were kind of looking for, but things were really exaggerated. The crust was overly burnt. The toppings were kind of right. The base wasn't quite right, but we knew the kind of building blocks were there. So this concept of having a circular heater kind of at the edges of the pizza was something that, we kind of latched onto. Taking this back to Sydney, I remember on a bus ride back from the factory, I had this idea to, we needed to elevate the elements so it wasn't so close to the pizza crust. But then if we did that, we were going to be compromising the interior. So where your delicate mozzarellas and your delicate basil is, that we needed something like a barrier. And that was where we came up with this idea of putting a circular heat shield, basically inside that heater. And what that did was focus or concentrate the energy that heater was producing onto the area of the pizza that we wanted it, so onto the crust. Certainly some of that convection heat, like just the hot ambient environment, would be cooking the pizza, but that really intense radiant energy was being applied where we wanted it. And what that resulted in these were the first couple of pizzas. Again, not the best pizzas in the world, but they were exactly kind of the characteristics we were looking for. So we got some leapening. The interior of the pizza was still kind of preserved, so you had mozzarella. The basil was still green. And it kind of was a proof of concept that sort of combination of heater, shield, that was something that we could kind of go forward with. Now, if we compare where we ended up to the other options we had, so with a wood-fired oven, obviously the hot oven's extremely hot, but that direct source of radiant energy comes in the form of the fire to one side of the pizza. And that's causing the crust to blister and get that spotting, which is, amazing. It does require whoever's cooking this guy to go and rotate the pizza as it's cooking. Otherwise, you'll get one side absolutely burnt, the other side still undercooked. So it requires a bit of work and a lot of skill to kind of get this whole thing coordinated. What we were doing, which we didn't even realize at the time, I mean, we learned so much as we were going, but what we were doing with the initial prototype was basically putting that fire directly above the pizza in the form of like really intense radiation. And for some pizza styles, it was actually okay where you're using pre-grated cheese, but anything where you've got more delicate ingredients, by the time the crust had a chance to cook, the ingredients were totally obliterated. So it wasn't applying the heat how we needed it to. Whereas the heat shield, it kind of gave you the best of both worlds. You got a lot of intense radiation on the crust. The interior ingredients were protected, but still being kind of cooked from the hot ambient environment. And unlike a wood-fired pizza, you don't need to rotate the pizza because that heat was being applied all around. There's no need to rotate the pizza as you're cooking. One of the things, a really conscious decision early on, was this kind of question of a pizza maker versus a pizza oven. So that top image, that's the existing product that was in the market. And we felt that was very much a pizza maker. So something, it's almost a novelty product. And there's a whole host of pizza makers on the market. But we knew what we were doing and the tech that we'd come up with was different. It allowed you to cook something that you couldn't cook before. And we didn't want it to be a really awesome maker. We wanted it to be serious. We knew it was going to be expensive, so it had to look legit. So we were thinking how we could make it feel more like an oven rather than a kind of novelty product. And so that idea of a circular thing with a lift up lid, it's awesome for some things, but it doesn't scream pizza oven. It's maybe more like a waffle maker or a jaffle maker. And pizza ovens, when you think of that, they've got a cavity that you have to slide your pizza into, and a little sort of narrow opening. You know, there's that sort of, it's got a style which we needed to kind of try and, you know, capture in some way. So what we ended up coming up with is an oven with like a narrow door and a D-shaped cavity, so that you could slide your pizza in, and you'd get that same kind of feeling, you know, in a small way, to a pizza oven. When we took our heater that we'd developed and put it into that D-shaped cavity, we got this, where one side of the pizza was being cooked really well, but then the other side, of the front side, was undercooked. So the first prototype, we were using the existing pizza oven, which is a circular cavity. When we went and applied it to a D-shaped cavity, we were getting uneven results. And what that was due to, with the design of the cavity and this pizza oven feel, we'd effectively made an asymmetric cavity where the rear half was really highly efficient. So we had stainless steel walls wrapping around the pizza. Any energy that was being produced would be bounced off that, and it was really kind of nice and, you know, efficient. Whereas the front half was much less efficient. We had the sidewalls extending away from the pizza, the door where there was a glass window that was losing heat and losing energy. So we had to think of a way of how we were going to solve that. And where it started was we really simply just made two heaters. One at the back, which was a lower intensity, and one at the front, which was a higher intensity. So then we could, you know, really easily go and change the power, and get sort of fine tune and compensate for an asymmetric cavity. And this was, one of the pizzas cooked from that one. So we were getting, you know, really close to where we wanted to. The problem with that solution, and kind of where the product was at that point in time, is that it was, you know, with all these little fixtures and what we were trying to do was all too expensive. So we got to a point where, although everyone was super excited about the performance, we were pretty sure that it was getting too expensive and consumers wouldn't buy it. So we had to completely redesign it from ground up. One of the things that we redesigned was this heater that we keep talking about. And so rather than looking at the glass kind of carbon fiber heaters that I've shown you before, we ended up looking at really ubiquitous stainless steel heaters, which if you went to your wall oven or your home oven, you probably see a steel tube heater like this. They're really common, really durable, really well known and relatively cost effective. They don't have all the benefits of the carbon fiber ones, but in a big cost saving effort, this is where we wanted to look at. And within this, we basically went to the manufacturers of the heaters and tried to push that tech as far as it could go. Now, we had different discussions with them, got all sorts of samples made, but we still had that problem of needing to make one half of the oven cavity basically hotter than the other half to compensate for that inefficient or that asymmetric cavity. So what we came up with was the idea of kind of making two heaters in one. So we had one half of the heater at a higher watts density and a lower half at a lower watts density at the back. And what it looks like is this, where you get one half glowing really brightly and intensely, so burning super hot, and one half not glowing as brightly. And if you look at that under an X-ray, you can see, it's a little bit difficult to see, but I think you'll get it. So the front half there's a wire filament that's coiled throughout the inside of that stainless steel tube. On the front half of that, it's coiled quite tightly, whereas at the back, it's much looser. And that gives you basically two different temperatures for that wire to glow at. So we were working with very simple technology, but pushing it to its limit. And one of the ways we validated that was just by cutting out paper discs, putting them in the oven, burning them or scorching them, and trying to establish or figure out how even things were if we had hot spots where we might want to sort of shift power around. It was really effective. Okay, then with all of that work and trying to make a pizza oven, so nothing with a lift up lid, and optimizing to get the performance we were after, we'd created a usability problem. So to get the upper heaters close enough to the pizza so that you get the perfect amount of leopard spotting, it meant that they were relatively close to the pizza. And in an oven format where you're sliding a pizza in through like a little slot opening, it was a little bit difficult to do, particularly if you're not particularly skilled at pizza making. For some people it's okay, but really it's not a particularly user-friendly experience. And that's what's amazing about the existing pizza oven on top there. You've got a lid that you can open, you've got full access to the cavity and the stone, you can get in there, you've got lots of room to move. Whereas what we'd created, even though it worked really well, it was actually difficult to use. And so we went away and thought about how we might be able to approach it. And what we came up with is shown here in this little video. So what we decided to do was basically connect the deck or the cooking surface to the door. And it's just really simply through a couple of hinges. And then it's got some moving parts at the back of the oven. So when you open the door, the deck comes forward. So it's sort of presented to you, comes forward and lowers itself, giving you more access and feel like you can kind of, use this thing. But then as you close the door in cooking mode, the deck gets elevated. It becomes, the pizza becomes closer to those elements so you get the performance you're after. So this was, a really simple, MDF model that we made. I went down to Bunnings one afternoon, some butt hinges, really simple and crude, but it just demonstrated how we thought we might be able to solve the problem. And this was one of the things that generated so much excitement within the marketing team at Breville, and like the whole team really, because it was demonstrating technology. Imagine if you're in Harvey Norman or like wherever you are shopping, the units aren't plugged in. They're not sort of cooking pizzas for you. But if you've got something where you can open the door and something kind of happens, there's a bit of theatre, and you feel like there's some sort of obvious tech that's on display. So, if you can kind of capture those little things, it's exciting. So this was the direction that we ended up going with. Now, just to show you a little bit, these are some of the key prototypes that we developed through, or probably over a couple of years, but really within probably a 6-month window, most of them were made. Some of them successful, some of them absolutely not, some of them too expensive. But really the combination of these two, the first one being the performance proof of concept, and then the second one being just showing really simply how we might address that kind of key consumer problem. They were the two things that kind of got us there to then, or the catalyst almost for going ahead with the final working sample. So this is a model that was made, full working model, sorry, that was designed to be as close to what we intended to make as we could. So this had as many of the right materials, the right dimensions that then we could use and validate either by performance testing, checking that things weren't getting too hot, checking that we'd be compliant. So just putting it through its paces. So this prototype was a combination of soft tooled parts, fabricated parts, machine parts, and 3D printed parts. We did loads of testing, pulled it apart, trialed new things that broke or things that were being problematic. We'd get new parts in or redesign parts. basically learning as much as we could and getting as much confidence that what we would end up going into production with, at least most of the big problems were solved. And yeah, lots of testing. Now, a lot of Breville's products, so if you're looking at our ovens, our microwaves, I mean, obviously styling aside, they've got a really common feature, which is they have a door that closes and sort of seals off the cooking cavity. And then separate to that is a control panel where the electronics live. And that's for good reason. Electronics and heat typically don't mix that well. So with the pizza oven, we decided to put the controls in the door. Now, it was for a few different reasons. It was partly driven because, I mean, aesthetically, it's super clean. It's something that we kind of wanted to do, even though we knew it was going to be a major challenge. But it meant that the control panel didn't have to be in addition to the cavity. It could actually be positioned in front of the cavity, which made the footprint of the product smaller. So this was already a reasonably sized oven. And if we could make those controls on the front of the door, it meant that the footprint wouldn't be so big, therefore more appealing and taking up less consumer kitchen space. Although we did know it was going to be a challenge, particularly because the oven gets so much hotter than what we typically do. Unsurprisingly, things melted. We had issues where control panel housings were melting, PCBs were, components were dying, fans were overheating, the thing stopped working, you know, all sorts of problems. What we ended up doing was repositioning the cooling fan to underneath the product. So it actually sucks in air through the feet of the product and then ducting that up through a vent into the control panel. And by doing that, the fan could keep running all the time. The electronics stayed cool and problem solved. So gearing up just before tooling, we were still doing lots of testing, you know, as much learning as we could, but we're also, you know, really honing in on what the final product would look like. And this is a photo of the final visual model that we made. Now, I mean, Breville's aesthetic is, I guess, constantly evolving. When we developed this product, it was at the time where we were really starting to shift away from the kind of commercial aesthetic to something a bit softer. And this was our first attempt at designing an oven to kind of work with the then new Breville design aesthetic. And I mean, even that caused, you know, a whole host of challenges where we're sort of trying to make, you know, metal parts stretch differently to how they're used to being stretched, or how we're used to them being stretched. But yeah, I think where we got to was pretty cool, really. And finally, before we were just about to go to tooling, and we made a pretty major change. What we'd been developing up until that point was an oven that was really, really dialed in for making one style of pizza. So it was pizza napolitana, which is the hardest pizza to make, or it's the quintessential pizza. But there's a whole world of pizza, and what we were sort of really getting close to was designing like a unitasker. So we were thinking about what we should do, and without even testing it, we released and tooled with the idea of adding a second heater, which then we could control through electronics to either apply heat only on the crust of the pizza if you want that for pizza napolitana, or if you're cooking a frozen pizza, or if you're cooking a pan pizza or something else, we could then tinker with the power distribution and apply more even heat. So with the combination of, or the addition of one more heater, we sort of unlocked a whole world of food types or pizza types, which was untested before that. Then we went to tooling. Now, after tooling, we did a little bit of refinement and tuning. Pretty soon after, we took a sample over to the US and spoke with a few different prominent pizza people. So on the left is Kenji Lopez, who's a writer, or was a writer for Serious Eats, well-known sort of pizza enthusiast. We took it to Frank Pinello, who's the host of The Pizza Show, and runs a pizzeria in New York. Then we took it to this guy, Dan Richer, who owns Raza Pizzeria in New Jersey. And all the time, just talking to them, like demonstrating the oven, getting their thoughts, picking their brains about like, what do you think? What should we do differently? Just absorbing as much as we could. Then taking all of that back, we came back to Sydney and continued to kind of refine the product. But one of the big areas we were then sort of trying to update with those learnings was the interface. And the big debate was whether we would be kind of consumer-centric or prosumer-centric. And the difference being the consumers, we'd be talking about the types of foods, like a food menu. If you want to reheat pizza, if you want to do New York style pizza, just go and turn the dial and the unit will do the thinking for you. It'll tell you what time we suggest and kind of configure everything. Whereas what we'd been sort of listening to, the prosumers, they love the idea of being able to tinker with everything. So set their own individual deck temperature, set the dome temperature, because it's something that's really unique for this product. And it was probably the most contentious part of the whole project. What we ended up with was two interfaces, but primarily we were consumer focused because that's who Breville is. The primary interface was a food menu that consisted of a few different select pizza styles. Then again, the unit would do all that hard work, setting up power configurations, times, temperatures for you. But a really novel solution was still kind of catering to those prosumers, was the development of this hack mode sticker or hack mode magnet, which was a magnetic overlay you'd put onto the product, and then those dials change function to be that full temperature control. So someone can kind of do whatever they want to. So the tinkerers, the enthusiasts, we've still got something that they can kind of experiment with, but for most people, just turn it on and go, and it works. One of the issues, like I'm sure we created a lot of issues, but one of the issues, moving wires in hot environments, we had to go and find solutions for. One of the things that we ended up doing was taking, broken samples down to a Chinese hospital and x-raying them to try and figure out where the breakages were and trying to get to the source of the problem. A little bit unusual for Breville is that pre-launch we engaged with the pizza community. So there's, lots of, passionate people about pizza and blogs. We got on them and sort of introduced ourselves as, we're Breville, we're developing this oven. Because we saw threads starting to appear. Oh, have you heard about this oven that's coming? And we jumped on and just said, look, happy to answer any questions. They were super skeptical, rightly so, but we ended up talking with them, still do, and putting videos on YouTube, kind of just demonstrating the product in action in real time. And then lots more testing, making sure that what we'd be kind of delivering to consumers was going to be reliable and they get what they're after. So we launched, and we launched well. I mean, we got lots of 5-star reviews, lots of really kind consumers. We, really luckily won the Red Dot Design Award. We received the Australian Good Design Award. We had some amazing articles written about the products, being that, this was, I think, a personal favorite, which is ridiculous, but the countertop oven is the pinnacle of human achievement. Obviously ridiculous, but still cool. And we made it to this really quirky pizza museum in Chicago. But we had an issue where the stones were breaking. Now, we hadn't seen it before, and we basically put this together as a map of what we could do. And it was kind of two things. I'll skim through it, but we could either look to control the process, so how the thing's made, the factories, all their inputs, or we could control the design, which was really in our hands, like how the thing looked and, thicknesses. So we went down that path to start. We were analyzing like what's going on in the stone in terms of temperatures. And you can see, this is a graph just really simply showing that the front corners of the stone are much, much cooler than the rest of the body, which in ceramics is not a good thing. We took that learning and then applied, we ran that through FEA simulations, looked at the heat distribution, and then took that and created stress concentrations. And you can see that there's some red areas on the sides and the front. They're areas where basically the part's trying to kind of move and flex, and that's where those stress concentrations are located. And that aligned really well with the failures we were seeing in the field. So we thought there's something to do with the way temperature's being applied to the part, to the failures we were seeing. We then went to redesign the heater, the deck. We redesigned the whole sort of moving assembly and relaunched the product. So take two, we still had some failures. And it was better, but we hadn't cracked it that done. And what we started doing was looking for patterns, is there a kind of common theme to where these things are cracking? Is there a common use case that people are doing this mode? And, we were trying to kind of then replicate that. So we were, really destructively creating little fires inside the oven. We were, really, poorly using this thing. We were transporting them in the back of cars. And it was proper car mechanic syndrome where we knew the failure existed, but we couldn't recreate it. So, without being able to recreate the problem, it's really difficult to fix. We did recreate it when we hit it with a blowtorch, but that's not really the point. We then proceeded to go and visit factories, talk to them, understand, the whole host of what they do, what we might be able to control. And really, it wasn't until we took some samples over to the University of Western Sydney, to their material lab, and analysed what's going on at sort of a molecular level or, structural level, that we understood a little bit more about what's going on and what we might be able to fix. So very quickly, it looked like the glaze. So these pizza stones have a glaze on them. It looked like that may have been part of a contributing factor, but more interestingly, we had the substrate or the base layer. We had it run through this X-ray diffraction process, and that spits out a chart like this, where you start seeing what phases are going on within the stone, or within a material. Really interestingly, what we found was that the stone that we were making, it looked a lot like, we were seeing the presence of these little peaks, and that looked a lot like a stone that had been fired at 1150 degrees, which from what we understood was not high enough. So the materials, like all the raw materials we were putting in, they weren't being fired at a hot enough temperature to allow the kind of transformation and the formation of the new material that we were actually looking for. Why that's important in our case is that those particles that we were seeing, they have a coefficient of thermal expansion much, much higher than the rest of the material. So it means that as that pizza stone heats up, generally the whole body wants to heat up or expand a little bit, whereas those particular particles that we were seeing in higher quantities than we would like, they want to expand a whole lot more. So effectively, the pizza stone was kind of trying to tear itself apart from the inside just by heating up. So with that information, we ended up reworking, talking with the manufacturers, and ultimately, touch wood, I think we've solved the problem, which is amazing. And lastly, so over the last couple of years, which have been pretty challenging for everyone, we've heard of a couple of stories which has been, really humbling. So, as nice as design awards are, and certainly consumer feedback, hearing those kinds of things is amazing. But we've heard of, more than a couple of stories where the pizza oven has somehow kind of helped people. So the image on the left is from the Vice channel, so their Munchies program. There's an article about this woman who, in New York City, she used to cook pizzas professionally, and she gave up her job and then basically started cooking pizzas out of her kitchen to help. She charged what anyone wants to pay for them, but basically would give them away for free to anyone who might be out of work due to COVID, maybe financially struggling, whatever it is, but she just cooked them for free. And then the image on the right is a comment from a guy who, again, over in the States, had lost his job and basically had no real job prospects as far as I know, and ended up using the pizza oven to start a new career and feed himself and, basically sell pizzas. And that's got him going again. So, as nice as everything else is, I thought that, it's pretty amazing to kind of hear that can happen from something you develop. Thanks very much.
Thank you, Michael. That was quite a story. Whoa, whoa. I don't know where to start, but it's just amazing.
Cool. All right.
Yeah,
Thank you very
yeah.
much.
So everyone, we still have some time and you can ask your questions to Michael via the chat. I love the part where people that were out of job because of COVID could establish a new job.
Yeah, it was amazing.
Pizza maker. How many people do you know have done that?
Oh, we've got a PR agent in New York, and he just said, like, shared a couple of articles with us. He said, look, he's heard of many, but I don't know. But no, it was really lovely to hear that kind of thing. It's certainly not why you kind of develop a product, but to hear that, it's amazing.
Definitely amazing. So here there is a question from Nicholas, and he asks, how is the work divided between industrial designers and engineers? Did the engineers take over a lot of the analysis work, or do you work together to come up with the mechanical solutions?
Yeah, so I worked really closely with mechanical engineers, like the core team, and like we've obviously got different skill sets, but there was no hard division or saying, look, no, this is your job, this is my job. Even like the FEA studies that really are probably stretching the limits of what an industrial designer does, we were involved. Yeah, so definitely as collaborative as you can be, and that's kind of, I think, part of what led to the product.
Yes. The next question is, as a designer, how have you collaborated with the company team?
With the company team?
That's from Özlem.
All right. Yeah, so Breville, it's a pretty big company now, and there's a lot of talented people in there with different backgrounds. And yeah, like I think that's part of what makes Breville, and again, this product, like just talking to as many people as you can, including as many people, the more you can, the better. So, I mean, there's people who specialize in design, there's people who specialize in food, as much, just bring everyone in. And really that's the recipe.
And Özlem's question go on, and she says, if the designer is a consultant designer from outside, did you have any consultant designers in the team?
No. Oh, yes.
Okay. Daniela is asking a quick question. How long did this project take from when you jumped onto it to the first, then the second launch?
Yeah, sure. So I joined in 2015. We launched in 2018. So at the end of 2018, so maybe 3.5 years. And then I think we relaunched the better part of a year later. And yeah, then some mopping up to do at the end. So it probably went for 5 years or so, on and off. But yeah, it's quite a journey.
Next question is from Jake. How much influence does the marketing team have in the design process, and are they also quite involved in a collaborative sense?
So in Breville, at least, we've got a go-to-market team, and they were certainly involved in some of the high-level planning, but not particularly involved in the design process. They got excited when they saw things, and they, we spoke to them about what we were developing and how that might kind of work at launch, but they weren't particularly involved in the design process. But then within the core team, we've got some category managers who aren't necessarily marketers, but they're involved in more the strategy, and they were certainly involved in helping us manage costs and helping guide things. So yeah, a little bit involved.
Next question is, what's your favorite pizza?
Look, honestly, they're all good. The pizza Margarita is pretty well hard to beat, really. But yeah, I'm no pizza snob.
I have a follow-up question. Were you still able to eat pizza after the project ended?
Absolutely. Yeah, like quite often at Breville, when we're developing a product, you eat that much of it that you can't stand the sight of it anymore. And honestly, for some reason, pizza is this magical food that no one on the team got sick of. Like we would have done, I don't know how many thousands of pizzas, honestly, and still more than happy to eat one.
Okay, so I'm conscious about the time. We've hit the 1 hour mark, and the questions seems to have stopped. So thank you so much, Michael.
No problem.
I really want to extend a heartfelt thank you for presenting this wonderful story to us and generously sharing all the little details, juicy details behind it. It's a fantastic story. But I also think that most of us are craving pizza now, so we'll see how we go. And to all of you who attended this evening, thank you for joining us and making this evening even more special with your questions. And stay tuned for the details of the next invitation to the 5th talk, which will be on the 4th of July. Until then, stay well and safe. Goodbye. And thank you again, Michael.
Thank you.